Hi, my name's Cass. I'm the newly elected auditor of TPSA. I want to say thank you for joining us on our first talk. We have Professor Manya Sahni here. She's new teaching here, but she's a veteran TP. And so we might ask her about how her experiences with TP were and how she's moved on through postgraduates and is now back at Trinity as a teaching fellow after the talk. But I'm not going to spend too much time out talking. I'll kind of let you introduce yourself. But yeah, afterwards we might go for pints or something. Nothing really organised. So do you want to go ahead?
Sure. Thanks so much for the introduction and congratulations on being elected auditor. It's my pleasure to be here. So just a quick little introduction about myself. So I did theoretical physics in Trinity as well, quite a few years ago now, not that long ago. Afterwards, I moved to London to Imperial College to do quantum field and fundamental forces, the Masters. I'm not sure if any of you are in fourth year and have been looking at it, but if you have, chat to me about it. Got lots of opinions. After that, I went on and did a PhD in Black Hole Entropy and Supergravity at King's College in London as well. After I finished my PhD, I went and I did a teaching fellowship at King's for 6 months, UCD for a year, and now I'm at Trinity. Just really bizarre to have lunch with your old lecturers, but it's quite exciting. Okay, so I'm going to tell you a little bit about black hole entropy and supergravity. Before I start, just so I know how fast to go / slow to go, I just want to get an idea of the distribution. Hands up if you're first year. Okay, good. Second year? Third year? Fourth years? Masters. PhD, okay. Postgraduate, okay. All right, I'll go nice and slow then. In this case, okay, so the content of this talk is roughly going to stay the same though. I'm going to introduce what black holes are. I'm going to talk about some aspects of quantum mechanics that are relevant to our following problem, which is what are the quantum effects on black holes, how black hole radiation can occur. This is going to lead us nicely into an analogy between black hole mechanics and thermodynamics, which is often referred to as just black hole thermodynamics. Afterwards, I'll kind of give an extension on how to view these ideas in string theory and supergravity. And lastly, I'll hopefully get time to give you a quick overview of what my PhD would have been on. Okay, so black holes. Right, so what are black holes? I think we all know this anyway from just popular science, otherwise you wouldn't be in this room. So they're things that exist in the sky. They have a strong gravitational field, so strong that nothing can escape, not even light. Okay, I always have to ask people, what do you think defines a black hole? What do you think actually, you're used to your theorem-proof definition world by now. What do you think is the defining part of a black hole? Any guesses? Fourth years. No, you haven't done GR yet. Yeah?
Is it the Schwarzschild metric?
That's an example of a black hole, but the Schwarzschild metric can also describe general space where you don't cross that certain Schwarzschild radius. In that case, it's just describes the space around a massive object. Yeah?
High mass, small radius.
High mass, small radius, exactly. That's a really good way of looking at it. In fact, there's a critical limit, which is the Schwarzschild radius, and that is the critical limit is what defines a black hole. So a lot of people think black holes are just singularities. They're points where things don't make sense. Not really. The definition of a black hole is it's an object which has an event horizon. Essentially, there has to be a certain area around the object. If you get into that area, there is no point of return. That's what defines a black hole. Okay, so if you have what's called a naked singularity, one where there isn't a horizon, you can go right up to the little center of the black hole. That's not actually called a black hole, that's just a singularity. Black holes are objects where there's some area around them, some region around them. Once you reach that region, you can't come back, essentially. Okay, so quick review. So the way we all see light is because light bounces off of something, and then it bounces, scatters, comes into our eyes, and we see that object. Okay? So for that to happen, what actually has to happen is whatever object that your light is shining on, the light should be able to escape back out. Now, black holes first come about as an idea when you start looking at essentially there being a speed limit, speed of light. Okay, so if you want to look at it from a very kind of school method of analyzing things, you can go back and have you guys done Leaving Cert Physics? Yeah, okay, everyone's nodding. Okay, great. So you know the word escape velocity? You need a certain amount of velocity in order to overcome the gravitational potential energy of the surface you're standing on. Okay? Now, if you keep making that gravitational potential energy bigger and bigger and bigger, you're going to need more and more escape velocity to get out. Eventually, the amount of escape velocity you need to get out is going to equal the speed of light or start exceeding the speed of light. That's the first idea of a black hole. It actually predates quite a bit general relativity. It starts with somebody coming around and saying, well, okay, escape velocity exists, but what if we take these limits so that essentially the escape velocity goes to infinity? What happens there? And classically, there was no problem because there was no maximum to speed. The second you have a maximum to speed, you have a black hole, hypothetically. Okay, so with that said, actually you can actually derive the Schwarzschild radius just doing that analysis of escape velocity. All right, this is the first photograph of a black hole. They exist 100%. Okay, usually we're used to seeing them as these large objects that exist at the center of galaxies. They're called supermassive black holes, or we're used to seeing them or describing them in terms of a massive star died and what it left behind was a black hole called a stellar black hole. Roughly, just to give you some numbers, stellar black holes, this is going to come up later, they have masses of about 10 to the, well, our sun is 10 to the 30, it won't turn into one, so let's go at 10 to the 31-ish. Okay, actually I'm just going to be neat and just call it 30 because I don't, with theoretical physics, rough numbers is good enough. Okay, so stellar black hole, and your supermassive black holes are about 10 to the 35 or so. Okay, a couple of thousand stars, a couple of million stars, maybe 10 to the 37, but again, I'm trying to keep neat numbers, 35 is good enough. Okay, now there's another class of objects that can be a black hole. Okay, so you might have heard of them. They're sometimes called early universe black holes. Have you heard of that before? Okay, so it's hypothesized, completely not proven because it's hard to prove, that essentially you could have had a third category of black holes when matter wasn't quite distributed as nicely as stars and planets. Everything just existed in a big ball. Different areas in that big kind of plasma gathered more and more mass, found a critical ratio of mass and radius, and became tiny black holes. Okay, there is that class of black holes. There is, so smaller black holes, or question mark? Okay, I'll leave a question mark there. Okay, the other option that I'm sure you guys have heard about or seen in news at some point, CERN's going to create a black hole. It's going to smash particles together and it's going to do all of that, and it's going to create an area where the mass is so big and squished into such a small area, you're going to be able to form a tiny black hole again. Again, hasn't happened. Okay? So they're kind of our categories of black holes, but I'm going to come back to this in a while when I start talking about where we're at. Okay, so this is the first photograph of a black hole. Okay, so you're doing your undergrad at a time where this photo came out, probably when you were doing 4th or 5th year of school, I'd say. Right? No. Yeah? Yeah. So this is amazing for me because in my time, you know, they hadn't even done the LIGO experiment yet, so they hadn't even observed gravitational waves and black holes smashing into each other. The only evidence of a black hole until 2016 was there was a star that was fluctuating in a way that was unpredictable, somewhat. However, when they modeled it, shrinking, not fluctuating, shrinking in something of an unpredictable way. Okay, Cygnus X1, there was a famous bet between Hawking and I think it was Cable You can look at the bet later on, whether or not it was a black hole. But everyone thought it was possibly a black hole, stellar black hole, where it was a binary system. That black hole died, that star died, started eating its sibling. Okay, but you couldn't be sure. So were black holes real? We didn't even know till 2016, which is quite recent if you think about it. But now we have evidence that they exist because when two smashed together, we saw the gravitational waves. Then secondly, we actually photographed one. And by we, I don't mean me. Okay, so history of gravity and space-time. Okay, so where do black holes come from somewhat? Okay, we said a little bit on it. Isaac Newton, sat under a tree, apple fell on his head, usual story, realized things fall down, things attract each other, they have a mass, everything attracts each other, and so on. So Albert Einstein came around and he viewed this slightly differently. Okay, so essentially, if you imagine, what he imagined was that the apple, the Earth forms a curve, a dip in space-time. So if the apple isn't being held at the top, it has to fall into that dip. Okay? So essentially what he said was mass is a property of space-time. Okay? The heavier something is, curvature is a property of space-time. The heavier something is, the more it curves the space-time continuum. So I'm sure you've all seen this picture before. The kind of heavier your object is, the more it causes a dip. And just like if you can imagine, because you can't imagine in 4 dimensions time curves, but if you do imagine a regular sheet, if I forgot to bring my scarf, but if I have my scarf down here, I throw an apple here and I throw a tiny pencil here or something, it will roll towards the apple because the apple would have created a dip. That's essentially the idea of general relativity. These massive objects create bigger and bigger dips, so other objects are going to fall towards them. Okay? The heavier the mass, the higher the curvature. Okay? So gravity isn't just a force pulling things down, so don't tell your mechanics lecturers, but gravity isn't a force just pulling things down, it's this extra thing, it's a property of space-time. Okay? Now, where does this come from? You'll have to wait till 4th year, but I'm going to give you a rough general idea of where it comes from. The rough general idea, really quickly, is just from the fact that, well, okay, so you've done, everyone knows F equals ma, everyone knows F equals mg, mg being m times gravitational acceleration. Okay, that is actually a much more profound thing than you think, because other forces outside of gravity, they also have a constant which shows you how the proportionality constant. Usually for electromagnetism, for example, it's charge. The fact that gravity has the same proportionality constant as the mass is the thing which appears in how things accelerate, how things move through space. This is how the original idea for GR actually came in to Einstein's head, which was just that, well, okay, mass is somehow related to how things move, but it's also related to gravity. So how things move should be somewhat related to gravity. And he put those two together. Okay, so that's the rough idea. Okay, so now that we've already done black holes and GR, we can move on to quantum mechanics. Okay, so quantum mechanics, as I'm sure you've heard before, it explains the behavior of what's going on at a very, very small scale. So, for example, for atoms and molecules, it gives us all the underlying rules for chemistry. So it better be right, because otherwise chemistry would tell us that it wasn't right by now. It's got a very different nature to general relativity. For example, it tells us that everything is based on probability. Okay, so even from that itself, they're two completely different theories. Okay, everything's based on probability. All right. Now, in quantum mechanics, there are two types of particles. Okay, there are particles which carry your forces. They're called bosons, and particles which carry the mass, or the matter, which are called fermions. Okay, so force carrier. An example of a force carrier would be the photon, carries the electromagnetic force. Okay, and example of matter would be electrons, protons, neutrons, whatever you like. Okay. Now, the big problem with quantum mechanics is we don't know how to unify it with gravity. There are many theories that try to unify gravity and quantum mechanics out there, Some more popular than others, but it's not a solved problem. Okay, it's the biggest unsolved problem somewhat. Okay, so this is what I need from quantum mechanics. So I'm just going to ignore everything else in quantum mechanics and move on to this particular process. Sorry, just looking around. I don't know. Yeah, okay, we're good. I thought some of my master's students were coming and I wanted to make them answer this question, but I won't. Okay, so you've heard of antiparticles. Antiparticles are particles which have the same mass and quantum numbers as a particle but opposite sign. Okay, so by that I just mean I'm going to use the most common example, electron and a positron. Electron and positron have the same mass. Electron has a negative charge of minus 1.602 by 10 to the minus 19 coulomb. Your positron will have the same mass as the electron, but it has a charge of plus 1.602 by 10 to the minus 19 coulombs. Okay, they're somewhat opposites in a sense. Now, that's the only quantum number charge that I'm discussing here, but there are other quantum numbers out there that you're going to study in quantum mechanics as well. They're always opposite signs. Okay, so now, whether it's classical mechanics or it's quantum mechanics, all processes, or theories of quantum gravity, all processes should conserve charge and mass / energy. Okay? That's just a universal thing that we have agreed on, and hopefully it never breaks down. But conservation of mass, energy, and I say mass / energy because they're both the same thing under E equals mc squared. Okay? So that's our basic thing. Now, there are two quantum processes that are going to be relevant when we look at black holes. Okay, the first one is pair creation. So essentially, pair creation is when you have a boson, so like a photon, is traveling across space. At some point, it splits into an antiparticle and particle pair. When it splits into those, we don't violate anything because the coming photon has energy E, splits into something which has mass m, another thing which has mass m, so as long as E is equal to 2mc squared, we're good. Okay, and then because the two particle and antiparticles have opposite quantum numbers, you're not violating any other conservation. Okay, the net charge, photon has 0 charge, electron has plus E, positron has minus E, other way around, add them together, you still get 0. Yeah, so pair creation's allowed in quantum mechanics. Pair annihilation is another process. This is when a particle and an antiparticle come together and they basically annihilate each other. Okay? When they annihilate each other, the energy from their annihilation, 2mc squared, goes into the energy of some outgoing photon. So this is kind of represented in this diagram here. I can't read. Oh, I can't read. Okay, good. So this is like your photon comes in, splits into an electron and a positron, for example. They come around, they re-meet at this point. When they re-meet, one goes up, the other one goes down. When they re-meet, they kind of combine, and then they go back out. Okay? Now, so everyone okay with pair creation, pair annihilation? Yeah? Okay, good. So, the vacuum is what we need next. So vacuum, when you hear of a vacuum in classical mechanics, it's a region devoid of space. Space devoid of matter. Okay? There's nothing in it. It has energy equals 0. But there's a problem here, which is Heisenberg's uncertainty principle. So I'm going to switch to that because the vacuum fluctuation makes me a bit dizzy. Okay, so you've heard of Heisenberg's uncertainty principle. You've heard that you can't tell the position and momentum of a particle at the same time without some uncertainty in one or the other measurement. Okay, if you're saying you know position exactly, then you have no idea about momentum and so on. There's another equivalent version of that. Third years might have done it by now in quantum mechanics, which is energy and time. Okay, you can't say for sure that a particle at a specific exact time has a particular energy. There's some uncertainty in those measurements too. Okay, so essentially a vacuum is a vacuum, but because of the uncertainty principle in quantum mechanics, the vacuum, you can't say for sure, has 0 energy at all times. Okay, it does overall, but because of the uncertainty principle, it can have non-zero energies at different points. So the vacuum's not a vacuum. What happens in a vacuum is this kind of the error in the energy that error means there's some minimum energy there at some point. Can be specific about the time because we're not being specific about the energy. There's some specific energy. Your particles borrow energy from the uncertainty principle. They come into creation, okay? They annihilate each other and they go back, okay? So this would be like the diagram I drew, only there's just nothing on either side. There's nothing coming in, nothing coming out. Two things form, they come together, they annihilate each other. That's it. These are called vacuum fluctuations. And so empty space isn't empty in quantum mechanics. Empty space is full of particles creating and annihilating themselves all the time. Okay? So quantum mechanics breaks down a lot of the things that we think are definite. Okay, so this is your vacuum, and it's just things moving around essentially all the time. But when you observe it, the uncertainty principle allows it to fall back to zero energy. Okay, so what do vacuum fluctuation mean near black holes? Okay, so I already said to you guys, we don't have a theory for quantum gravity. We don't know how to describe gravity or black holes in a way that's conducive with quantum mechanics. So what we do, what people did in the 70s somewhat, was they looked at what some people call semi-classical physics. Okay, so you take your black hole, you treat it like it exists in general relativity. Okay, it's a point where space-time curvature is infinite, nothing can get out, so on. But you treat the area around it like it's full of a quantum mechanics vacuum, okay, where there's fluctuations and everything going on. So this was what occurs if you think about vacuum fluctuations happening near black holes. Okay, so thought experiment for us. Okay, a virtual pair. Oh yeah, the ones that are popping in and out of existence, they're called virtual pairs. A virtual pair forms near a black hole. Let's say the antiparticle forms just a little bit closer than the particle, and it falls into the black hole. Okay? That's this here. It's called a Hawking particle. The particle, however, is just that bit far away and that it's able to escape. Okay, one is close enough to the horizon, gets sucked in, the other one escapes. Okay, so that's what a vacuum fluctuation near a black hole can look like. You can see all the lovely diagrams. Now, what does this mean? How does this give us problems? Okay, sorry. I hope nobody saw the next slide because that has my answer to my question on it. Okay. Let's start with just considering our processes that should be conserved. Okay, mass of the black hole is capital M. We're going to pretend our black hole isn't spinning or anything like that, okay? It's got no other energy. The mass of the particle, antiparticle, is little m, okay? Energy before the process of the black hole and the area around it is a vacuum, is just equal to mass of the black hole times c squared. Okay? Now, my particles have borrowed energy from the vacuum. Okay, they've come into existence. Energy after. So what does it look like after? It looks like I still have the black hole, but I have this extra little particle that's escaped. Okay? So this process, a vacuum fluctuation occurring near a black hole, can cause energy conservation to fail. This is a problem. We want energy to always be conserved. Can anyone think of a solution? How do I make these two equations equal?
Black hole emits something.
Yeah, the black hole loses some mass. It loses mass equivalent to capital M minus little m. That will fix everything, right? There you go. So Stephen Hawking came along and said, see, all these little thought experiments, this is one of my favorite things about theoretical physics, that the big ideas are always really simple at their core. It's just always good to sit and reflect. Okay, so Stephen Hawking's idea was the black hole must lose mass equal to m. The other way of examining this exact same thing, forget you know about quantum fluctuations, okay? We aren't quantum mechanics anymore. We are classical mechanics people. Okay, so we're in a black hole. This just looks like a particle was just ejected from the black hole. Okay, we don't know what's actually going on. Another way of thinking about this is that the black hole spontaneously emitted a particle. Okay, so with that said, we've discovered a process by which things can escape black holes. It's completely spontaneous though. This loss of mass by the black hole is called Hawking radiation. Okay? This isn't observed yet. CERN are looking. I'm sure that LIGO and other people are also looking, but I know CERN are looking. Okay? Yeah?
How are they looking?
Good question. We'll come back to you. Okay. Okay. So let's move on to black hole thermodynamics. I will come back, I promise. Because I'm going to show you the difficulty. Okay. So, actually, I will come back now. So, black hole evaporation. If black holes radiate, they will eventually evaporate. Okay, if something's losing mass, eventually it'll lose all its mass. Okay, I'm not going to do any of the calculations that get into this equation, but I really love this equation. There's a few equations I love, so I'm going to have to include them in this. One of them is the time taken for black holes to evaporate. Again, this is an approximate formula which ignores quite a few things, but it's roughly equal to this. Okay. Now, one of my reasons for loving these formulas is, look at all the constants in it. It's got, pi doesn't matter, g, so it's got gravity. It's got h, so it's got quantum. It's got c, so it's got relativity. So this truly is a result which has to do with quantum gravity, essentially. Okay. Now, the reason I picked this is because I wanted to show you a problem with this. Okay. Why have we never seen a black hole evaporate? Okay. So, well, let's look at our categories of black holes. So our first category is stellar black holes which have a mass of 10 to the 30. Okay. Ignore my other constants. Their order of magnitude doesn't even matter. If I have an m cube here, okay, mass is to the order of 10 to the 30. It's going to get cubed. It's going to be 10 to the 90. Sure, that's in seconds. Converted to years, it'll be 10 to the 83-ish. Okay. How old is the universe? It's like 13 billion years, right? At least it was when I was here. No. But it's nowhere near that order of magnitude. We've got a long time to wait if we're going to be waiting to look at a stellar black hole evaporate. Supermassive black holes, 10 to the 35, it's even worse. Okay? So our third option, this is where your question comes in. Smaller black holes. Okay. Smaller black holes. So we have atomic particles smashing into each other. Okay? When they smash into each other, they might create a black hole. We might see it evaporate. Let's see if that's actually possible. Well, does anyone remember roughly electron mass? It's like order of 10 to the minus 31. Thank you. 27 is proton, isn't it? Yeah. Okay, let's do protons because I think CERN smashed protons. But 10 to the minus 30, let's just do that because it's easier. Time to evaporate, m cube. 10 to the minus 90 seconds. Yeah, we're not going to observe that. Don't think so. 10 to the minus 90 is not a lot. However, so basically they're just not in existence for long enough for us to observe them or for them to do anything significant, really. But however, the one thing is they should suck in a lot of energy and they should release it very quickly. So quickly that maybe there's some hope. So essentially that's how you look for black hole evaporation or signs of these tiny black holes. No look yet. Because again, that's just outside of our range, essentially, right now. Okay, so that's my note on black hole evaporation. Let's move on. Let's talk about black hole thermodynamics. They realized interstellar is more fun, I think, because I think that's next door, right? I swear it's not. No, it probably is. Actually, I hate that movie. But anyway, let's not go there. I think all black hole physicists do. Right. Except, yeah. Okay, so black hole thermodynamics. So if something radiates, if an object radiates, it must have some temperature. Objects which have temperature, now we can start talking a little bit more about thermodynamics, but if something has a temperature, you guys have probably learned, first years have probably also learned by now, temperature means you have some entropy, you have some thermodynamics going on there. Okay? So if a black hole radiates, it must have some idea of temperature and entropy. Predating Hawking's ideas, there was another man who came along, Bekenstein. He was the first person to propose that there would be a relationship between the entropy of a black hole and area. Okay, I think first years can also answer this, but maybe second years. Generally, when you think about entropy of an object, it's usually proportional to which other characteristic of the system. Forget temperature. It's always, which ones do you see? You see pressure, don't care about pressure. Temperature, there's a third one. Volume, thank you. Black holes doesn't have a volume, it has an area relation. This leads to all sorts of exciting things. Call someone else in, maybe I'll think of someone good. But essentially, this leads to holography. It leads to us thinking about life existing outside on this kind of surface of a region. Okay, it leads to all things cool. Anyway, don't worry about that. So the relationship between entropy and area was first proposed by Bekenstein in 1973. It predated Hawking before 1975. So I want to talk about how he did it because it's just really interesting. So what he did was he considered the loss of information when a particle falls into a black hole. Okay, lack of information means an increase in entropy. Okay, entropy, if you want to think about it in terms of information theory, is just chaos. Okay, so the less information I have, the more entropy I have. Okay, so when a particle falls into a black hole, we lose some information. We lose at least one bit of information. An answer to one yes or no question, which is, does the particle exist? We don't know. We've lost one bit of information, minimum. Probably a lot more, but one bit at least. Okay, so then he computes using a calculation relating general relativity and my fourth year project that nobody picked. Sorry, no, it's okay. But essentially, a particle falls into a black hole. As it falls into a black hole, there's an increase in the area of the black hole. Okay, there's an increase in the entropy and there's an increase in the area. That's what he showed. It's not an increase in volume, it's an increase in the area. All right. More interestingly, what he showed is if you take the particle to be a point particle, there's no increase in area. Entropy 0, whatever. But quantum mechanics again comes in and tells us that each particle has some kind of wave nature, has some minimum wavelength, the de Broglie wavelength. Okay, some people are nodding, good, they've seen that before. So there's some finite size that you have to have for every point particle, minimum de Broglie wavelength. So if you let that equal to its size, that's when you get out this formula. Okay? So that's why the result doesn't happen if you do classical mechanics analysis. It only happens if you do quantum. And that's where the quantum nature comes in this case. Okay, again, one of my favorite formulas. It's the Bekenstein-Hawking entropy formula. So S is for entropy. Kb is Boltzmann constant. A is area of the black hole. Divided by 4 times L Planck squared. L Planck is one of my, this formula is generally my favorite because it has even more constants in it. It's got G, H bar C cubed, so you got gravity, you got Planck's constant, you got special relativity, and you've got thermodynamics as well this time. So it really uses everything. Okay, so, one sec. Before I move on, this associates some sort of entropy to our black hole. Okay, along with it comes laws of thermodynamics that are equivalent to some laws of black hole mechanics, some conservation of energy things, and so on and so forth. Entropy can only increase, similarly area can only increase. Okay, by some finite processes. Okay, now, in thermodynamics, when you have entropy, okay, so this is where we're going to take a little bit of a step up, so if you're not following, don't worry, you're not being examined on this anyway. In thermodynamics, you can model entropy of a function as a sum of the states that make up that system. Okay, have people seen this before? Statistical mechanics, you've started seeing this a little bit more. Okay, great. Okay, you can usually write entropy equals Boltzmann constant times log of n, where n is the number of states that give you the same energy. Okay, the same system. Okay, this raises a good question, which is, can we model the entropy of a black hole as a sum of the microstates of the black hole. Okay, which leads to many, many questions like what's a microstate of a black hole? So microstate of a system, states of a system would just be the various particles and the states they can be in. Okay, you just add them up, throw it into the formula, and you're done. So what can a black hole be made out of? Okay, so to answer this question, we're going to need a theory of quantum gravity. Now, my chosen theory is string theory and supergravity. Currently the most popular is string theory. So let's talk about it just a quick little bit. But keep this question in mind, okay? Can we write the entropy as Boltzmann constant and log of some number of microstates of our black hole? Okay, so string theory, I'm sure you've seen a very, what's the word for it? Popular science introduction to it before, but I'm going to just give you one anyway. Particles in string theory are extended objects rather than point particles. Okay, what that means is you have one-dimensional objects, they're called strings. Two-dimensional objects, like a little plane moving along, they're called your branes. You can have three-dimensionals and so on. Okay, so you can't break them down anymore. They are your particles. Okay, particles are strings or they're two-dimensional surfaces and so on. Okay, it turns out that consistency requires there to be a lot more extra dimensions, usually 10 or 11, depending on which theory you're in. There's many string theories. So where are these extra dimensions? Well, these extra dimensions are curled up, usually it's called compactified, into some kind of ball type of shape. Okay, the usual picture people give is, isn't it? It's like it's an ant walking on a pipe. Okay, to it the world seems like it's two-dimensional because the third dimension is curled up there. Right. Okay. So that's kind of the picture there. So what's supergravity? Well, first of all, let me tell you what supersymmetry is. Supersymmetry is a theoretical symmetry between fermions and bosons. What that means is fermions and bosons can turn into each other. There's some relationship there. Photons can turn into electrons and so on. There's some, not photons, electrons, they're not pairs. Sorry, they're not a supersymmetric pair. But particles that are force carrying can be converted into particles that are matter carrying and vice versa under the symmetry. Okay, why? Why do we want supersymmetry? Especially because we're not finding it in nature. Why do theoretical physicists find it so hard to give up on supersymmetry? Well, because of a few things. First of all, they make vacuum fluctuations make sense. So especially the fourth years, you guys have started doing QFT, you've probably seen quite a lot of vacuum diagrams that make you really sad because you have infinities everywhere. Supersymmetry takes care of them. Okay, take my word for that. Okay, the other reason we like supersymmetry is because there is a no-go theorem which tells us that the only allowed symmetry, apart from the symmetries of the standard model that are your symmetries of space-time, plus symmetries between particles, okay, the only other allowed symmetry is supersymmetry. Okay, that's the only allowed thing. If it doesn't exist, then we're done. Standard model has already got all the symmetries. Supersymmetry itself is a theory, supergravity itself is a theory where you say that there's this relationship exchange between fermions and bosons, this supersymmetry, and you add to it general relativity. Put them together, you get supergravity. Okay? It takes care of quite a lot of the bad behaviors of general relativity of gravity when you look at it in quantum mechanics. Okay. So, quantum black hole entropy. So this is like the last slide, which is going to be a little bit on my PhD. So what did I do? First, what did string theorists do? I'm a supergravity person. Okay. So what string theorists did, this was 1996 or 8, around then, they modeled extremal black holes, it's a type of black holes, as made up of stacks of strings or branes. Okay? They computed the number of microstates that you would have in order to make up a certain black hole. They plugged it into the Boltzmann formula, and they found that they got the same entropy as the Bekenstein-Hawking entropy for a large area. But not only did they find that they got the same at leading order, they found some corrections. Okay. Corrections in log A plus 1 over A plus order 1 over A squared. Okay? If area is large, 1 over A becomes a really small number. Log A is also large enough, but it's not too bad. essentially for large A, these terms kind of vanish. So we wouldn't see them if you just consider semi-classical situation where you have black holes described by GR and quantum particles. But you do see them if you start looking at string theory and proper theories of quantum gravity. Okay, so semi-classically, we can ask, where did these higher terms come from? Okay, well, one of the answers is higher derivative gravity. I think I'm talking to the PhD students. Okay, are you theoretical physics PhD students?
No, condensed matter, but...
Okay, has anyone in here done general relativity before?
Yeah, I've done.
You've done GR. Okay, I have two people that are still listening. That's great. But you know the way when you do GR, we always work with theories that have second derivatives. Actually, this should work with everyone. When you do mechanics, you always consider theories with second derivatives. Lagrangians are always partial mu phi squared, right? We don't do more than second derivative theories. Yeah? Higher derivative theories do exist, perfectly valid. Okay? Now your Lagrangian can depend on higher derivatives. In this case, you can actually reproduce some of these corrections. Okay? But not all of them. So we do need to do a deeper analysis. So last page now, black hole entropy and supergravity. Okay, so first of all, I want to tell you about the ADS-CFT conjecture. Okay, this is a duality between certain theories of gravity, very popular these days, in n dimensions, and certain quantum field theories in one less dimension. Okay? So if you have a 4-dimensional gravity theory, some gravity theories, you can map it to a 3-dimensional quantum field theory. Okay? Currently, this is the most popular area of study, essentially, because it gives us quite a lot of interesting things to analyze without having to resort to supersymmetry or string theory, although supersymmetry and string theory also use ADS-CFT all the time. Okay? Using ADS-CFT, we can also calculate the same black hole entropy including all, and I say question mark, quantum corrections, because this is a bit of still a question mark. Okay, if we just consider ADS-CFT, can we actually get the same black hole entropy corrections, these log A 1/A terms, as you would get if you did string theory? So you expect to match the results from string theory where it's known, and you should be giving predictions for what string theory will say where it's not known. Remember I said there's many string theories. So different cases, different dimensions, different compactifications. We don't know what the black hole entropy would look like, but this doesn't care. You can literally just do ADS-CFT, get the calculation down, you can give predictions. Okay, so that's what I did. I worked on a certain class of black holes in 5 dimensions. 5 dimensions. That's the part I don't care to admit. And we calculated what the black hole entropy corrections would be, and we overall tried to compare it to the string theory results. And so far it's looking quite promising. In 4 dimensions, they've already done this for multiple types of black holes and actually have found that it's giving the same results. So ADS-CFT seems to be reproducing string theory, which is good. Nice to have things that are agreeable. All right, so that's what I was working on myself anyway. Sorry, one more thing. I also say give predictions because one of the other additional things we were able to do was, because we were studying black holes in a lower dimension theory, you can embed it into a higher dimensional string theory and predict what that string theory should say the entropy of that black hole should be. So we actually were able to make some predictions for some black holes as well. Right, thank you for listening. Any questions?
So I was just wondering, you were saying that supersymmetry can fix a lot of problems. How exactly?
So how exactly is a good question. So you know you have like your vacuum fluctuation diagrams.
Yeah.
Essentially, the kind of supersymmetric pair produces the exact same vacuum fluctuation but in the opposite direction. So when you add them together, they just cancel out. You don't have to do anything else to get them to cancel out.
Okay.
That's kind of how it makes all your vacuum fluctuations fine, essentially, that's how.
And given that supersymmetry hasn't been observed at CERN, what energy scales are we expecting it to appear at?
We can keep going. As in, like, basically there's a mechanism called supersymmetric breaking. which allows us to promote the masses of supersymmetric particles to be higher and higher, just like the Higgs mechanism. It's the same kind of idea. You get more and more mass for supersymmetric particles, and theoretically, I mean, they could have really, really high masses, in which case you can never restrict the supersymmetry out. So we always get jobs. Joking. But yeah, I think we can still keep it.
Well, that's just a free parameter that you can choose. Okay, I see.
It's quite tunable, yeah, exactly.
Okay.
You can just increase it. There's new models coming out to increase it further and further all the time.
And so in this, the ADS
CFT
correspondence working out for you, doesn't that imply, I mean, isn't ADS to do with negative curvature?
Yeah.
Do we live in a negative curvature universe?
No.
Okay.
We're theoretical physicists, we don't care. ADS CFT, okay, so I'll tell you where it's useful. So where I would have used it in particular, because I was doing things which are not measurable at all, but which aren't too far from reality. Okay, miles away from reality, but okay. So essentially, if you have black holes, a particular class of black holes called extremal black holes, you might have studied them in theory. If you look at their near horizon area is also described by ADS. So that's where you can use ADS CFT. So there's different pockets of space essentially where ADS is the right metric, in which case ADS CFT should work. There are also people, actually one of my colleagues at King's was working on an equivalent de Sitter CFT theory.
Okay.
Yeah, so that's happening, but it's less well behaved. I don't think there's much on it yet.
Alright, so because around the black hole, ADS is kind of...
ADS becomes the metric near the black hole horizon.
So you've reason to trust those corrections?
A little bit, yeah.
Yeah, okay. So.
But again, extremal black holes are extremely unrealistic. So.
What's their deal again?
Mass is equal to charge for the black hole.
Okay.
Roughly. I'm ignoring some units there.
Okay.
But you're not going to you don't have naked charge anywhere. You're not going to have a black hole that has enough charge to equal the mass, right? It's completely unrealistic. But there's also some spinning black holes that can also be extremal, which are some hope there, but I don't think there is much. Again, you're trying to get the black hole to spin as much as its mass, which is kind of ridiculous. Probably violating something.
Sure.
Yeah, extremal, not realistic. But then, because you have these ideas for extremal black holes, what their entropy could be, you can do expansions to near extremal black holes.
I see.
You know, and then you get something. It's not totally. Yeah.
So since with the ADS CFT correspondence, you have the difference in dimension between the two, how can you use that to extract kind of real-world information on the assumption that the world just doesn't lose dimension depending on what framework you're working in?
Yeah, so you would go from ADS 4 to CFT 3, for example, right? You do your calculation, then you come back. It's a duality between the fields in ADS 4 and a duality between the fields in CFT 3. So you map over to them, then you map backwards, and you go back to the 4-dimensional theory. Similarly, if you're working in a quantum fields theory that's in 4 dimensions, you map over to ADS 5, you do your calculation in gravity, and then you come back. So what it does is it allows you to calculate things in the extreme quantum region and extreme gravity region using the other one, in one less or one more dimension. There's actually quite a lot of work on ADS CMT at the moment, condensed matter theory, ADS 5. Again, I think one of my friends did a bit of work on that. So that's another topic which is kind of becoming popular and measurable, which means that we might know if ADS CFT isn't just a conjecture soon. Yeah?
Is there an argument to be made that because supersymmetry was never observed at CERN, that every theory that bases its argument on supersymmetry should be strictly ignored from now on? Do you think CERN itself is maybe looking at the wrong way, or do we have found an experiment? Or
personally, I think this is personal opinion here, but well, like, look, I can just get the easy cop out and say, like, look, they just don't have high enough energy levels yet. Once they get higher energy levels, we'll see supersymmetry, and it will all be okay. That's what we tell ourselves at night when we do PhDs in supergravity. The answer is, it's just, I mean, people should be and are looking at alternatives to string theory. String theory needs supersymmetry, okay? In order to have a string theory which includes fermions, matter, which it better include, it needs string theory, the supersymmetry. So you'd have to throw out all of string theory. Until somebody starts coming up with better alternatives to string theory and supergravity, people are looking at, there's no point throwing them out. Somebody's got to keep looking and hoping for the right direction.
Might we be biased by having this type of philosophy that we need to look for this? And for example, if this wasn't the explanation, then we might be only looking in the wrong direction to find the correct direction. If you see what I mean.
I mean, it's just in a sense that there's no other option. If you get what I mean, like, so what you can do, for example, and actually, if anyone is doing a PhD in the near future in this type of topic, I think the region that kind of is looking at this is they're called effective field theories. You consider kind of weak gravity theories, weak quantum gravity theories, essentially. Okay, they won't be able to describe things which have a high mass like black holes or anything. But people are looking there and they're trying to find some interesting results and see if they can give us something enlightening. But like, honestly, I think, yeah, it's hard because there isn't anything yet. Maybe somebody will come along and come out of the box and invent something completely different and we'll all be like, oh shit, been wrong for years. But it is what it is right now. Like I said, there is a no-go theorem that says you can't expand the standard model with any other symmetry. So that kind of shuts off a massive way that we add particles to a theory. Yeah. So hopefully they'll just find it and we'll all be good. Standard model seems to be working though. So like we're only really at this, okay, black holes were first thought of or first came up in 1918 I think. And we only found out that they're real for sure in 2016. So, people probably back then were like, why even bother? Like, we're never going to be able to measure something like that. So maybe there's hope. We don't know. Experimentalists in the room, help us. All right. Yeah.
The no-go theory you're just talking about, is that an assumption we've made that we're working off, or that's something we found?
No, that's actually a mathematical theorem, essentially. It's called the Coleman-Mediola theorem, if you want to look it up at some point.
But that's based on the standard model that you found?
Yeah.
Okay.
It's just saying from the standard model, there is no other symmetry you could add. All right. Questions?
What would happen if a graviton was thrown into the mix? Like, how do you discover it?
So gravitons they're kind of people who work with quantum theories of gravity, like weak effective field theory descriptions of gravity. That would be gravitons. Gravitons would be the particles that are the force-carrying particles of gravity, essentially in the quantum framework. Okay, so just like photons carry electromagnetism, they would carry gravity. They also appear in string theory, where they're supersymmetric partners to some other particles called gravitinis and so on. So they do appear. They appear as little particles that disturb the structure of space-time, but that's how you would view them. So essentially, gravitational waves, which we viewed as just a disruption in space-time, would be made up of tiny little particles called gravitons. But it wouldn't throw anything really up. Yeah.
And you mentioned just before that the standard model was working just fine for the moment, but there have been some results in recent months that show some results that could be explained yet with the standard model. Am I understanding wrong?
I think. See, they're so recent. I wouldn't get caught up on it just yet. Like, do you remember there was the Grand Sasso? Were you guys physics following folk by then? I don't know. Maybe you remember the Grand Sasso one. They had particles, neutrinos that traveled faster than the speed of light. Yeah, you guys remember? And we were all like, whoa, this is it. And like, oh my God, they've checked so many times. It was wrong. There was like an experimental error. Somebody lost their job. It was horrible. But like, so I kind of leave it to about like, until it's verified by a good few different organizations, which is why it's important not to have just CERN, but to also have DESI and Particle Accelerator, Fermilab and all them. It's good to verify each other's results and figure out somebody hasn't done something silly. Yeah. Any other questions? That's
Actually, just on that note about CERN, has everyone here signed the petition to try to get Ireland to CERN?
Yeah.
Has anyone not signed the petition, actually? Just like to have an idea of our audience. No? Alright, that's sweet.
Actually, just yeah, on the point of CERN, we're going to start a mailing campaign, as in having people like mail letters or emails their TDs, the local representatives, because there needs to be a like sense. They need to feel a sense of momentum, so that when they're chatting amongst themselves in the Dáil, that oh yeah, I got a couple of letters about CERN. Oh yeah, shit, so am I. You know. So yeah, we'll be looking into that, and I'll have more details next Tuesday with the next seminars, and we'll probably send some information out in the next newsletter. So just so you know.
In 2012, there was a very similar campaign run by theoretical physics students as well. Yeah, that was it. Ask Sinead Ryan, she was very helpful. Back then, Twitter and all those things weren't quite as, well, they still were big, but the power that students have was a lot less realized. So like really do kind of, we did gather a few people, but it definitely wasn't enough to change anyone's mind. We got like Sinead involved, and I think it was possibly written in some newspaper at some point, students campaign, blah, haha. Don't do that to yourselves, just get a lot more people involved and really circulate it. It's good to sign it. Good work.
Do anyone have any questions about doing postgraduates in the UK or trying to become a teaching fellow or anything like that?
Yeah.
What precisely are your thoughts regarding that master's course in?
My first thought is that we're very sheltered in Trinity. I hope that it's still the same, but I don't think that we're very competitive here. At least I know from the lecturing standpoint, you're absolutely never marked on a curve. Nobody will mark you down because, 20 people already got A's, so they're going to give everyone else B's and C's. They don't do things like this here. They do there, and that results in a little bit more of a hostile environment. Although, aside from King's, I think it's the same in Cambridge and Oxford and Imperial. They have quite a bit of curving of students, which is very, very annoying because it just makes an atmosphere where people don't want to work together and so on. That's my first thought, which is the negative. The positive is they give you so many more resources than Trinity do. We had every single lecture recorded. We had lecture notes, LaTeX for every single course we took. Not for all the masters. Some of the later masters ones were taught by people who were less interested in teaching and didn't do anything even though they were required to. But for the most part, we had great sets of lecture notes, great assignments, tutorials, everything, like really, really well supported. But it didn't make up for the lack of atmosphere, at least for me. But I think overall it's a really good master's to go into, especially if you're coming out of the 4 years of theoretical physics here, because you're actually lining up to do some modules you've already done and then do some new ones, which is a really good lineup because master's years are really, really horribly hard. It's like the worst year. Third year of theoretical physics is similar. But yeah, sorry, third years. It gets better, fourth year's nicer. But master's is really horrible because you're trying to apply for PhDs, go to PhD interviews where people are asking you questions on modules you're doing right now. You could be taking general relativity, you've just learned what a Schwarzschild metric is, you go in the next day and somebody's like, get on the board and show it to me, and then you can have a job. So like, it's really high stress and stuff. So it's really nice to come out of Trinity where you've already done some of the modules already. You're putting yourself at a better place somewhat for it. So that would be the benefits. The downside I already said. That would be my thoughts. PhD was great though, but it completely depends on your supervisor. I think you guys would say the same. I had the best supervisor in the whole world. If anyone's ever looking for a PhD in Black Hole Thermodynamics, his name's Samir Murthy, he's at King's. Do have to do supersymmetry, but he's a great guy. It just really depends. The main thing I would say is any advice to anyone going for a PhD is just find out from people who've been their previous students if that person is going to be nice, if they're going to give you enough time, are they going to give you enough support, are they publishing enough? All of these things are really important to find out. Okay. Any other questions?
For the non-TPs in the room, is that master's program applicable to physical sciences course, you think?
You'll find it harder. It'll definitely be harder because there's the diff jom, QFT, GR modules that you do in the first term. You've already done those, and QFT and GR I think are mandatory. So you can't get away and learn new things. So you end up competing for the same grades with people who've already done those modules, which makes it a lot harder. Again, because they curve you, so you just have to work a lot harder. But essentially, no, there's nothing stopping. We had loads of people who came in from different modules. So we literally had people who came in who did experimental physics, didn't know what classical field theory was, trying to do quantum field theory. And then we also had people who had done full-on masters in different countries and had come over to do the same masters, repeating modules, just hoping to get slightly better marks so they could get a PhD. So it does curve around, it just, you can work hard and get over the hump of it, but it is definitely tougher. Classical field theory is the main thing, and quantum mechanics, but I think you get that in physics anyway.
I don't think you get CFT, I think you just say quantum.
Yeah, I think you just get quantum mechanics, right? But then you would probably get enough quantum mechanics that you won't be horribly with. But that's just one module to catch up on. So a few summers of work, or one summer of work, dedicated work. It's not outside the realm of possibility. One of my friends, actually, let me give you a positive example. One of my best friends who did, one of the best in her year now, she did her master's part-time over 2 years. This is another thing people do. They take the part-time over 2 years, and then they don't work during those 2 years. They treat it like full-time. So she did that. She came in from experimental physics, wouldn't have done field theory, didn't really have much quantum mechanics either, but she was actually one of the best in her year. So it's totally possible.
Yeah, I had a friend that he did his undergraduate in chemistry and went into theoretical physics,
Yeah.
I think in King's, actually.
Really? No?
Yeah, master's, I think.
Oh, that's not. Yeah, the King's Masters is good. I wouldn't recommend the King's Masters over the Imperial one for a few reasons. I've taught on it before, so I can tell you they don't give you as many resources. Certainly I had no pressure to. The good thing about it is we don't mark on a curve at King's. It's a much more of a welcoming place. It's like, come everyone, yay, learn together. But also the lecturers are a little bit more, they have a lot more freedom in what they can give you in terms of resources, which means you get less resources always. Yeah, but King's is good. King's is good. Do you know what? The other advice I can give you is if you are looking at masters, look at people more than anything else. Even at master's level, look at somebody who's doing something interesting there that you'd like to do. Maybe 2 or 3 people that are doing something interesting. And then if you see 2 or 3 people doing something interesting, then try and do the master's there and then approach them to do projects with them, because that's a great way to get a PhD with someone that you think is doing something cool.
Do you have any experience with any such research groups in mainland Europe, not in UK?
Mainland Europe. So I would have worked quite a bit with a group in Trieste, in Italy. So that's in ICTP. They're all really fantastic. I don't know about the masters. I wouldn't have known much about the masters, but I think their PhDs were generally basically the same level as the UK. So usually I think in the UK you might get an extra year because you're not expected to have done a 2 years masters, research masters, whereas in mainland Europe you somewhat do 2 year research masters. So you kind of come in with a little bit more than a PhD, but then an incoming PhD student, but then you're expected to finish earlier. So you'll want to balance that out. So you don't want to end up doing 1 year masters and then do 3 years PhD because you won't have enough time. Any other questions?
Okay, so I want to say thanks on behalf of the TPSA and the 40 people that are here. So, yeah.
Very impressive.
Thanks again.